In this video, we're going to figure out how to calculate probabilities of various poker hands. So how are we going to do this? Well, before we can actually find the probability, see what is probable, we need to look at the possibilities, which is the count of each of those various poker hands. Now, just real briefly here, in a game of poker, you're dealt 5 cards from a standard deck of cards, 52 cards, and using combinatorics we can determine the number of possibilities of distinct 5-card hands, which is given here is using the factorial notation. 52 choose 5, which amounts to 2,598,960. Again, these are distinct, meaning different poker hands. Now, the order of these is not important. So it's just the content of what you're dealt is important, not so much the order of them. In other words, if you swap the 10 and a jack with a jack and a 10, it's the same poker hand. Now, the factorial notation here, I'm actually showing you what the factorial notation is right in here, the usual. N choose k is n factorial divided by k factorial times n minus k factorial. Now, having talked about that, I'm going to provide the highest ranking to lowest ranking poker hands in this video. So again, in a standard deck of cards, just for clarity, there are 4 suits: club, spades, hearts, and diamonds. And there are 13 ranking or denominations or values, if you will. These range from ace, which we denote by letter A, through king. So 2, 3, 4, 5, 6, 7, and so on. Now, ace could be high. In other words, ace could be placed after the king, and that would be like the highest card in the poker hand. So let's actually do this. Let's go through and see how this is going to turn out. The very first poker hand we're going to look at, this is the highest. Now, the highest means the most valued poker hand in the game of poker. And usually the most valued hand is the least probable. As you can see, the probability of this categorization, which is a straight royal flush, is the highest, again, you can get in the game of poker. It's going to be very decimal, right? It's going to be about 2 in 1 million chance of being dealt a royal flush. So in other words, if they dealt you 1 million hands, you would expect 2 of those to be dealt a royal flush. So a royal flush is when you have ace through 10 in any one of the suits, but they all must have the same, they must belong to the same suit. Well, so how many royal flushes are there? There are what we call 4 choose 1. Right, the 4 here is because there are 4 suits. So you can have all, in this illustration, you're looking at the royal flush where I chose clubs as my suits. So it could be any one of the 4 suits: clubs, diamonds, spades, or hearts. Okay, so there you have it. There's 4 of them. So this one's pretty easy. Now let's take a look at the next one. The next categorization is a straight flush. This is the second most important dealt hand in the game of poker. A straight flush is when you have 5 consecutive cards or in a sequence that are in the same suit, but they cannot be a royal flush. So in other words, there's no ace before king here. So we're excluding a royal flush. So how many of these are there? Well, first of all, if you take a look at possible straight flushes, those could be ace, 2, 3, 4, 5. Then you have 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, and so on. The highest one you can have is actually 9, 10, jack, queen, and king. Okay, so there's 9 of these straight flushes. And again, because there are 4 suits, remember these have to be in the same suit. So there are 9 choose 1. That gives you the sequence of 9 possible straight flushes. and 4 choose 1 is the number of suits. So there are 36 of these. It's more probable than a royal flush. And the next item on the list, the next categorization, is that of 4 of a kind. In 4 of a kind, as you can tell, there's 4 of the same kind, same value, same rank, or same denomination. So in this illustration, my 4 of a kind, I have 4 aces, and then the 5th card could be any one of the remaining 12 denominations in any suit, right? So how does this work out? And I'm just going to actually begin to write some of these. I try to write these in combinatorics notation because that's usually how this is done. But it just looks nicer. But then I can also write these in another way, in the counting fashion. So for 4 of a kind, again, the first the first denomination, if you will, that we can have, these. It could be any one of the 13 denominations, right? So I could have 13 times, and then the remaining card, the 5th card here, could be the remaining 12 denominations. And then because there are 4 suits, could be any one of those 12 in the 4 suits. So there you go. That would be just for this 5th card. The 13 is how many ways you can have 4 of a kind, the first 4 cards. Okay, and then you put these together and it adds up to 36. So that's how many actually, I'm sorry, that's not right. That's not gonna be 36. That should be 4 of a kind. That should be 624. Okay, 624. So I'm glad I caught that one. Okay, so that's the number of 4 of a kinds. Now, let's move on to the next one. For this next categorization, we're going to... So remember, I corrected this one. This was 624. Okay, so please make a note of that one. Now let's continue on to the next one. I'll come back and correct that one. The next poker hand we talk about, number 4 on the list, is a full house. A full house is when you have 3 of a kind and a pair. The probability of this is about 1 in 1,000. Okay, so in my illustration again, my 3 of a kind, the 3 is 3 tens, and the pair, I chose a pair of 4s. So just like before, for the first 3 cards, it could be any one of the 13 denominations. And there you have it. That's the number of those. So how do we get to this again? Let me write this down in a fashion that we can follow a little easier. So there are 13 denominations. That's how I can choose. Instead of 10, I could have picked a jack, king, queen, whatever. So there's 13 of those. That's how many you can choose. Now, for any 3, for any 3 denomination or values we choose, because there's 4 suits, there are 4 choose 3 that I can choose just the 3 cards. Okay, and then I have 12 remaining denomination to choose the pair from. So it's going to be 12 remaining denomination, and because again there are 4 suits, 4 choose 2 is how many ways I can choose my 4. So I could have, for instance, a 4 of hearts, 4 of diamonds, 4 of hearts, 4 of clubs, and so on. That's what this counts. And this total is correct. There's going to be a total of 3,744 full houses. Okay, next we're going to move on to a flush. So a flush hand is when you have 5 cards in the same suit, but they are not consecutive. Remember, if they become consecutive, then that would create a straight flush or a royal flush. Okay, so how are we going to do this? Well, here's a combinatoric notation for the number of flushes. So the 13.5, let me show you this. So the 13.5, this part of it gives you the denominations, right? So for example, we can have 4, 5, 10, 8, 7. So that's how many different denominations the 5 cards could be selected from. And then because they have to be in the same suit, so this, in my illustration, they're all spades. These could be all diamonds, all hearts, and or all clubs. So there's 4 ways to do that one. Okay. Now, what is the subtraction here? The subtraction here is actually, this is the number of straight flush and royal flushes. So we're subtracting out royal and straight flushes out. And that's why we have the subtraction. And when you do that, the total is going to be 5,108. And I'll show you how to, what we already did. Let me go back up. Remember the number of royal and straight flushes we had? Okay, let me recall what they were. For the royal flush, we had 4 choose 1. For the straight, we had 9 choose 1 times 4 choose 1. And that is when you combine these two, you're going to get that expression. I factored out the 4 choose 1, and that's how I got the 10 choose 1. Okay. Now, 5,108 flushes. Next is we're going to straight. Okay, so let's take a look at number of straights in a poker game. So what is a straight? A straight is when you have 5 consecutive cards. This time they have to be in different suits. Okay, so they cannot be all clubs, all hearts, and so on. So that's why they have to be in different suits, but you cannot have a royal flush. And I recall what a royal flush was. And nor can you have a straight flush. Okay. Probability of this categorization is about 4 in 1,000. Now this one is slightly more elaborate as far as the combinations of how many there are, but for the let's see, this is for a straight again, right? Okay, so there are 10 straights, right? There are 10 of these sequences. 10 of these sequences. And you can list them. You can go from ace, 2, 3, 4. Remember, these are in different suits. And for example, ace, 2, 3, 4, 5, that would be one possibility. And then 2, 3, 4, 5, 6 would be the next one, and so on and so forth. Okay, so there's 10 of them. The 10th one would actually be that last one is going to be 10, jack, queen, and king, and ace high. Remember, this is a royal flush, right? So we're actually taking out, that's where this is being taken out here. See, we're subtracting it out. Okay, so the one just before it, which is permissible, is going to be 9, 10, jack, queen, and king. All right. Now, because these are supposed to be in different suits, so that's why each of these 4 choose 1 is. Okay, so for any one of these choices, for example, the queen I have, this could be queen of hearts, diamonds, clubs, or spades. So that's where the 4 choose 1 comes from. Same thing for the next one, and the next one, and this is for the last one. Okay. There are 10,200 of such poker hands. All right, let's continue on. Next. All right, let's take a look at 3 of a kind. With 3 of a kind, we have 3 cards of the same denomination. So for example, here I have 3 threes, right? These 3 threes could be, of course, any one of the 13 denominations. So for that reason, we have 13 choose 1. That's how many ways you can choose from among
the denominations. And within each of these, because remember, there are 4 suits. So for example, there are 4 threes in different suits. So there are 4 choose 3 ways that we can select the threes in this case, or whatever the denomination might be. Now what I have here on the right side, this would be the ways that you can choose the remaining 2 cards. So for example, remember you've already selected one of the 13 denominations, so we only have 2 denominations, 12 denominations remaining. So 12 choose 1 would be my next one. Okay, and again, amongst these suits, you could have diamonds, clubs, spades, or hearts. So that's where this other 4 choose 1 comes from. That's just for that selection. And then once you've selected the first, the second cards, denominations, then you only have 11 denominations remaining for the last one. And that itself could be also selected in 4 choose 1 way, be it any one of the 4 suits. Okay, now because the way I've done this in this segment right here sort of fixates that you choose this one first, that one next. But then we know that it doesn't matter. The order of these last 2 cards don't matter, right? You could have ace first, 10 second. So there are 2 factorial arrangement of these 2 cards within themselves that will give you the same poker hand, in other words, right? So for that reason, I'm going to divide by 2 factorial. Okay, again, this is one way about going about it. This is another way that may be a little easier, but both of them will give you the same results. With this methodology, I have 13 choose 1 way to select the first denomination, 4 choose 3 to make the selection of those from a suit, from a selected suit, because there are 4 suits. And then the last 2, we can say, well, there are 12 choose 2 ways to choose the last 2 cards, and 12 choose 2 actually accounts for the order. Order doesn't matter with combinations, remember that. So if I go the 12 choose 2 route, then I automatically am dividing by 2 factorial here. That's built into this formula. You see that? And of course, the 4 choose 1 is exactly what I have here. And that's, again, for each of those. There are 4 ways you can choose from among the suits. So both of these formulas will give you the same thing. And again, I want to emphasize that this part and what I have up here, this, and this combined, those 3 have exact same effect as 12 choose 2. All right, so however you do it, there are almost 55,000 combinations of 3 of a kinds. That's how many 3 of a kinds there are. And remember how I'm getting these probabilities, by the way. You divide this by total number of possible 5 card hands, with which I showed earlier there is about 2.5 million of those, right? That's up here. So if you divide each of these combinations, again, number of whichever we're looking for, by 2.6 million, you get the numbers, the probabilities that I have in front of every description of that poker hand. All right, let's move on to, let's bring up now 2 pairs. Let's move on to number 8, that is 2 pairs. So for 2 pairs now, right in here. For 2 pairs, that's when you have 2 cards from one denomination, 2 cards from another denomination, and the probability of this particular combination, 2 pair that is about roughly 5% of the times. Now, for this one as well, I've done it 2 ways. Let me center this first. Okay, got it. All right, so for 2 pairs now, if you notice here, I have a particular example or an instance of 2 pairs. So here's my first denomination. Here's the second denomination. You have 2 of each. Remember, within 6s, for example, there are 4 choose 2 ways I can choose my 6s. There are 4 choose 2 ways that I can choose my kings. So that's where these 4 choose 2s come from. It's for each of those. Now, because there are 13 denominations, so any particular pair there are 13 choose two ways I can select from denomination. So for example, I can go 5-8, I can go Jack and Ace, and so on. This particular example I have up here is 6 and King. So how many of these are there? There are 13 choose two. Okay, so that's where that comes from. And the last card, is only 11 denominations, right? Remember, there are 13 total. We've already consumed 2 of them with the first. Here's one, here's the second one. So there's only 11 remaining denominations. So of those 11 denominations, 11 choose one. Could be any one of those 11 ones. And then within each of the selection of a denomination, there are 4 ways, because there are 4 suits to do that one. And so there's that one. Again, this is the easy way to do it. The answer is there are over 123,000 two pairs. Now, the way I've done it up here, again, it's kind of like I did in number 7. I said, well, there are 13 choose one way to select the first one, right? And within that, there are 4 choose two for within the selection of denomination. Once I've chosen the first denomination, then there are 12 choose one way to select the next one, correct? But then again, the order of these don't matter. So in other words, I could have 6 6 King King, or I could have King King 6 6, and of course my last one is a 10. See, these are the same poker hands, right? So therefore I need to do division by 2 factorial arrangement of the pairs now, and this portion handles the last denomination. Now once I have that, the total comes out to be 123,552. Or, I could have done it this way, which is probably a more common way of doing it, but this is combinatorics, so you can do any way that you like, as long as you can kind of back up your methodology, or your reasoning, I should say. With this selection, again, I have 13 choose 2. That's how many ways you can select the pairs, right? So these particular pairs, that's there. Within each of these, there are 4 choose 2 ways to select each of them. And then 11 remaining denomination. 4 choose 1 is how many ways you can choose your 10, for example. Could be 10 of spades, diamonds, hearts, or clubs. And there you have this one. Let's move on to the next one.
Number 9. In number 9, 1 pair. That's the other possibilities of 5 card dealt. The probability of a pair is 42, better than 42%. So this is very likely to happen. We even have more likely hand, that would be number 10. But for now, a pair is simply 2 cards in the same denomination. But we cannot have 2 pairs, that's just 1 pair. So let's do what we did before. I have 13 denomination to choose my first pair out of, right? So that's going to be 13 denominations. For each selected 2, there are 4 choose 2 ways. This is among the suits of that denomination I can choose from. Then these 3 must be different, right? Okay, so the next choice right in here, that's going to be, let's see, it would be, I have 12 choose, well, let me do it this way. There are 12 choose 3 ways for these, okay, that I can choose the other, right? The other 3 cards, and each of those among the suits, there are 4 choose 1 ways to select each of the individual ones. Okay, and so that's how the remaining ones are selected for the pair. In all, there are 1,098,240 pairs. The probability of getting a pair is actually pretty high. It's about, again, 42%. Okay, let's take a look at our last possibility for the poker hand. This time we're going to look at the high card. So here it goes. Now the high card means just that basically you don't have any one of the other possibilities, numbers 1 through 9, those categorizations we looked at earlier. So your best bet would be whatever the highest card is in your hand. So in the example that I've displayed here, number 10, the high card is the 8 of hearts. Okay, so that is the highest card in my hand. As you can see, the probability over 50% of the cards dealt in the poker hands are pretty much not much. It's just a high card. So how do we calculate probability of a high card? I'm going to do this 3 ways. Method number 1, which is the easiest way out, is using the law of complements. Now, if you remember, the law of complements tells us, for example, if probability of rain is 70%, probability of no rain would be 30%, would be 1 minus that. So that's kind of what I'm doing here. So what I'm doing is to assess the probability of a high card, or actually the count of these, we're going to look at all possible 5-card hands and then subtract all the categorizations 1 through 9 above from it. And when we do that, we're going to come up with over 1,300,000 possible high cards. Again, this would be the easiest way out. And then there are 2 other ways. The next method that I'm going to show you is actually, let me display it, would be this one, which is also manageable. So what's the strategy here? Well, the strategy is to actually take a look at how many ways we can choose the first card, second card, and so on. Because there are 52 cards, so the first card could be any one of the 13 denominations, right, from all 4 suits. So it could be anything. So we have 52 choices for the first card. But because we cannot have repetition, because that will create pairs, 3 of a kind, 4 of a kind, and so on. So the second card, we only have 48 to choose from. So for instance, if our first draw was King of Hearts, then for the second draw, all the kings are out in all 4 suits. So that's why we are down to 48 cards to choose from. Once you choose your second card, again, by the same analogy, for the third card, we only have 44 to choose from. And the fourth one would be 40, and the last one would be 36. And then in step 2 for this method, we need to remove the order from our accounts. Because as I have displayed, let's say you are dealt a card, a poker hand that consists of 2, 6, 8, king, and 4. Doesn't matter what suit, but I'm assuming it's they're all in the same exact poker hands that you're dealt. So if you're given the 2, could be 2 of hearts. So in my second step in here, the 2 that you're looking at is the same 2. It's exactly the same hand. But if you rearrange the cards, it doesn't change the nature of that hand. So that's why we need to remove the ordering from it. So with 5 cards, there are 5 factorial ways you can rearrange them, put them in order. So that's why in the first part of the formula here, I'm dividing by 5 factorial. Okay, now from this, we're going to actually remove all of the various types of flushes. That's the straight royal flush, just a straight flush, and then straights. So, and those were found earlier, and then we get the same total, 1,302,540. So this would be the second method. The last method, which is kind of nice, I like this one because it's just more rigorous, and it uses counting techniques in combinations, also in conjunction with combinatorics, using combinations. So how are we going to go about this one? Well, initially for the first 5 cards, there are 13 denominations to choose 5 from. Okay. Now remember, these high cards, they cannot be all in the same suit, because if they are, then you get your flush. So 13-5 is how many ways you can choose the set of 5 cards, and then because each comes from a different suit possibly, so that's why we have the ladder part, the 4 choose 1 parts. These are for each of the first, second, third, and fourth and fifth cards. And then from this, we're going to take out flush, straight, and royal flushes. Now we calculated these again earlier in the previous categorizations. So that's what I'm doing. I'm subtracting those other types from it. And then we're just going to manipulate this sort of algebraically, which is really arithmetic. There's no algebra here. But the thing that we're doing that's algebra is basic factoring here. So what happens next? Note the 4 choose 1, because I have 5 factors of it. I wrote it as 4 choose 1 to the 5th. And that's what I have here. Next step, I actually distributed the negative to within the brackets. And the same thing here. And in this step, that's where you see this expression. And then you can actually cancel the last 2 terms in this expression. And let me do that. Hold on. There you go. Okay, so this is right in here. Notice these are opposites, right? So we can add opposites. They add to 0. And from that, you get, we go to the next step. And that's what that is. And what I've done here is I've actually factored out 13 choose 5 from that expression. And that would just simply bring these two together as one expression. And then from the last 2 terms, I factored out 10 choose 1, and that's what's in here. Okay, so that's what happens next. Let me remove these. Okay, and once I've done that, then as you can see, miraculously, we come up with essentially the same total as the one before. Again, I like this one because it's kind of got a nice combinatorics looks to it. And so that's how many ways you can have a high card. And of course, divide that by total possible, and that's how I got the what you call it, the 52% figure that you see up here, or 50%, not 52. The number that's up here, the 50%. All right, and then just as a note here, I was going to show you how this and method 2 and 3 kind of, you can make one look like the other. And more specifically, what I mean is the following. What's in front here, okay, the way we did it in method 2, you can actually create right in here. You can arrive at that using working what I had earlier, okay, using method 3, using my combinatorics notation. And to do that, I just pretty much played along with this expression. I rewrote it using, again, the factorial notation 13-5. Each of the 4, 1, 4, 1, 4 ones amounts to just 4. And then what I did is I multiplied the 2 fractions together here. And then I kind of grouped these 13 times 4, 12 times 4, 11 times 4, 10 times 4, and 9 times 4. I regrouped them in this expression. Okay. And then once I did that, well, 13 times 4, that gives me 52. So I got the 52 here. and then 12 by 448, and so on. And this is precisely what we had in using method 2. So it's just a different way of thinking about it, but the mathematics of it ends up being the same, regardless of how we do it. So with that, we are done with this video, and we did what we wanted to do, is to assess the number of possible poker hands and their corresponding probabilities. Okay, and I hope that you find this useful, and we are done with this segment.